So, oh, okay. So, if you flip the note packet over to the back, there is actually, wait a minute. Oh, okay. I guess you don't have that much space. All right, so I guess just watch me on this, okay? If you have space or somewhere on a blank sheet of paper you want to write this down. I didn't do this yesterday, but this is what you needed to finish the notes. Yesterday we talked about an exponential function, and an exponential function looks like y equals a times b to the x. And, you know, I'm in math lab each day, and Algebra 1 students are doing this. So I know for a fact you've done exponential functions. This is not new to you. So what you learned back in Algebra 1 is exponential functions have domain all real numbers. So, and you're going to see a beautiful connection to chapter 6 now. If I plug in negative 2, 2 to the negative 2 is 1 over 2 squared, which is 1/4. 2 to the negative 1 is 1 over 2, or 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. If you are sitting there saying, I don't know those negative exponents, you need to see me in office hours or come into math lab with any teacher, because I've taught that this year. It's been taught in Algebra 1. I'm not going to reteach it now in class, because at some point I have to hold you guys accountable. So here's the deal. Watch how this plots. I have 2, 4, 1, 2, 0, 1. Now negative 1 is up 1/2, and then you're going to estimate this. Again, this I'm just refreshing your memory from Algebra 1. You've done this before. And I'm just getting the cobwebs out. So here's what an exponential graph looks like. So the domain is negative infinity to infinity. Now let's talk about the range. Okay, range are the y values. Do you notice that I cannot come up with a value for x that makes it equal 0? Okay, what is 2 to the 0? No, 2 to the 0 isn't 2, it's 1. Like, there is no number you can come up with to put in the exponent that makes 2 to that power 0. So it never ever touches the x-axis. So watch how I write my range. It's 0 to infinity, okay? But it doesn't touch 0. Now, I have something called a horizontal asymptote, and we're going to abbreviate it HA. It's not ha, 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 ha. It's horizontal asymptote. The horizontal asymptote, in general, is going to be the x-axis. Well, that's in a line. It's y equals 0. Okay, so let's do it again with this one. If I have y equals 2 times 1/3 to the x. Well, let's go back to this one. Do you notice that's exponential growth? Growth is its rising from left to right. So we're going to see what happens here. Again, I'm going to do negative 2 to 2. All right, now this is going to get tricky with the exponents. So if I plug in 2 times 1/3 to the negative 2, if you have a fraction to a negative exponent, what does the negative exponent do to the fraction? It flips it, right? So it's 3 over 1 or 3 squared. Please excuse my dear Aunt Sally. I do the exponent before I multiply. Okay? Exponents before you multiply. That's 2 times 9. That's 18. Let's do the next one. 2 times 1/3 to the negative 1. So you flip the fraction. 3 over 1 is 3 to the first. That's 2 times 3 is 6. What's anything to the 0 power? 1. But that's 2 times 1. So that's 2. Then I take 1/3 to the 1 power. 2 times a third is 2/3. And if I square it, 1/3 squared is 1/9. 2 times 1/9 is 2/9. Again, if you're sitting there saying, oh my goodness, I don't know where any of those numbers are coming from, you either come into office hours or you get into math lab. Let's see, I don't want to go by ones because I don't want to get up to 18 that way. Let's go by fives. 5, 10, 15, 20. That'll do the job for me. So here we go. -2, 18. You're going to estimate where that is. -1, 6. 0, 2. Be careful when you're drawing an exponential graph. It's not going to touch the horizontal asymptote. So my domain is -infinity to infinity. I mentioned this yesterday, but I'll mention it again. The domain of all exponential functions is always all real numbers. The range can change, but for now, even though it comes from positive infinity to 0, that's not how we describe interval notation. Interval notation is always the smallest value on the left, the larger number on the right. It does come up from positive infinity and falls. So this is decay. It's falling. It is decay. But can anybody think of what could I do to a graph to make the horizontal asymptote move? I can make this one move. What do you do to a graph that would make a horizontal line move? Does shifting it left or right move it? No. Emma? Make what negative? I can flip it upside down by sticking a negative out front. You remember our U's? The U's that open up, I can make them open down. I can flip them. Remember? Left, right, up, down, stretch it, shrink it, flip it. Okay? So what's going to make the horizontal asymptote move? Flipping it wouldn't. Left, right wouldn't. What's left? If I shift my graph up 1, do you see the horizontal asymptote will go up 1. If I move it down 3, my horizontal asymptote goes down 3, like that. Okay? All right, so this is just real basic. So now we're ready to hit our notes. All right, an exponential function occurs naturally when an initial amount changes by a constant factor during a given time period. So if you look at letter A, is this growth or decay? Look at the graph. It's growth, okay, because it's rising. How about B? Is this growth or decay? Decay. All right, so we wrote this down yesterday that growth happens, growth happens in y equals a times b to the x if b is bigger than 1. Decay happens if it's b is between 0 and 1. All right, so we're going to talk about something called end behavior. Remember we did end behavior in chapter 5. It says, as x goes to positive infinity, as I move to the right, where does the graph go? Up. When x goes to negative infinity, where does it go? No, it doesn't go down forever. What's the y value it's going towards? No, negative infinity is down. It's leveling off. What's the y value? 0. Okay. In a decay, as I go to the right, where does the y value go? 0. Okay, it's not going to negative infinity. It never goes below the x-axis. And as x goes to negative infinity, as I move left, it shoots up. So recall from yesterday, f of x equals a times b to the x is an exponential function. So exponential growth is when b is greater than 1 and a is greater than 0. A is called the initial amount. And B is called the growth factor. The growth factor is 1 plus a percent of rate of change, expressed as a decimal. Domain is negative infinity to infinity, and range is 0 to infinity. Note, an asymptote is a line that the graph of a function gets closer to as x or y increases in absolute value. Wait, don't flip it yet. I want you to write something here. In general, the horizontal asymptote is y equals 0, and it has a y-intercept of 0, 1. This will change as we do transformations. All right, now you can flip it. Exponential decay. Exponential decay is f of x equals a times b to the x when a is 0 and b is between 0 and 1. Guess what? A is still the initial amount. And b is called the decay factor. The domain is negative infinity to infinity. The range is 0 to infinity. The horizontal asymptote is still y equals 0. And the y-intercept is 0, 1. But to graph these, you just make a table, negative 2 to 2, plug them in to get the outputs. All right, graphing exponential growth and decay functions. For each one of these, I'll do letter A with you in case you're a little unsteady here. Is this growth or decay? You look at the B value. The B value is 0.5. Oops. So this is exponential decay. The A value is the initial amount. And the growth factor, the B value, is 0.5. All right, try B, C, and D on your own. Okay, letter B, f of x equals 2 to the x. So this is exponential growth. What's A? I don't see it. Grace? It's 1. The B value is 2. So when you do y equals A times B to the x, if you have y equals B to the x, that meant A was 1. Okay, be careful with that. All right, how about letter C? Is this growth or decay? Jacob, what do you think? All right, this is exponential growth. The initial value is 3. B is 3.2. All right, letter D. Is this growth or decay? CJ, what do you think? It's decay. So this is exponential decay. And Cassidy, what's A? Good job. A is 1 and B is 1/3. All right, so no big deal. We did this a little bit yesterday.
Do we have to write exponential or greater?
You can do growth or decay. That's okay. All right, when you're ready, flip the page. And I believe you guys did this in Algebra 1 as well, so we'll just get the cobwebs out. Compound interest is an example of exponential growth and is interest paid on the initial investment and on previously earned interest. So I think you're interested in this because eventually, if you don't already have a job, you'll get a job and you'll want to set money aside for retirement. So when you retire, you want to live like you did while you were still working. So investing in things that will give you 3%, 4%, 5%. If you're lucky enough to get 8 or 9% sometimes, that's awesome. So this is the formula, and it goes like this. A equals P times the quantity. 1 plus R over N to the nt power, and I have something for you. This orange colored half sheet, as long as you keep track of it, you can use this on the quiz and the test. What? Absolutely. I've got a hole punch up here if you'd like. It's just a half sheet, so I didn't think it would hole punch very well, but you can sure give it a try. But this has a variety of formulas on it. Here's the exponential growth. The growth factor B is 1 plus R. Here's the compound interest. In a future lesson, we're going to do the PERT. It's called PERT. We're not going to see that one today, I don't think. I don't think so. No, we don't see it today. We're just going to do this other one. So A is defined to be the balance you want. P is the principal or initial amount. R is the interest rate as a decimal. N is the number of times you're compounding in a year. We're going to go over that. And T is the time in years. So, here, go ahead and fill these in on your notes. I do expect you to know these, okay? You should know that there's 365 days in a year. That should be common knowledge. You should know there's 52 weeks in a year. There's 12 months in a year. There's 4 quarters in a year. Semi-annually means twice a year, and annually is once. So you may not put that on the orange paper. You should know that. That's just common information. All right, when you're ready, let's flip it and do a couple more problems. So use the orange formula sheet here. It says, suppose Jenny deposited $5,000 into an account that pays 2.4% annual interest. Find the balance after 5 years. Oops, the daisy. So I don't know where this one went. Okay. So here's the deal. We're going to start with A equals P times 1 plus R over N to the NT power. Letter A is annually. So that means N is 1. So I'm going to do the first one with you and then ask you to do B and C on your own. So the initial amount invested is $5,000. The interest rate as a decimal is 0.024. Annually is 1. And then the exponent is 1 times 5. What I would recommend that you do is do the inside first and then the exponent. Then go to your calculator. Whether you use the OGT red calculator or your graphing calculator. I don't know that a cell phone calculator can do all of this. It might. Sure, certainly give it a whirl, but you can't use a cell phone on a quiz or a test. So we might as well practice your graphing calculator or your red OGT calculator. Money is always rounded to the nearest cent unless otherwise stated. All right, I'm going to pause, and I want you guys to do B and C. Look at what quarterly is. Plug in all the information.
Oh, that's because you didn't put 5,000, you did 50,000.
5,000 or 50,000? I wish that were close enough. Yeah. Sure, give me one moment. I gotta set this aside for a brain. T is years. Yeah, but it's not B equals. This is, the formula is A equals.
Oh, well, I
Yeah.
changed it to A.
There you go.
Thank you.
Alright, so letter B, quarterly is 4. So you're going to say A equals 5,000, 1 plus 0.024 divided by 4 to the 4 times 5 power, okay? So that's what you should have initially gotten. I do recommend that you can, if you have a graphing calculator, you can enter it just like this. It should be fine. This one, I got 5,635.46. Did you guys get that in B? Hoping at this point you got to B.
I got 5,151.
All right, let me take a look. Did you round anywhere?
Oh. What?
Oh, that. Yeah. Oh, you put it to the T power. It's NT. Quarterly is 4 times. There you go. Yeah, you guys, if you're not getting this, let's figure out the problem. This is to the, it's R divided by N, and then N times T. So letter C is pretty tricky with 365. That's daily. So I'm squeezing in here. On letter C, I got $5,637.46. So see if you're getting it correct with 365. Letter D says compare your answers from parts A to C. What do you notice? What happens the more often you compound? Don't you get more money? Oh, yeah, 29, 35, 37. So in letter D, the more often you compound, the more money it generates, which is really nice. And everyone you have all those parentheses.
Like I tried to even count.
So here's what I entered. 1 plus 0.024 divided by 4. Close that parenthesis. To the 4. Yeah, I don't know, you're doing too many parentheses. Yeah. I think, oh, you know how you entered this? You did 4 times 5 only to the 0.024 divided by 4. And it's 1 plus that to the 4 times 5. Do you see how you did that now? Alright, we're going to go ahead and stop there. Alright, so what I want you to do is I want you to take out last night's homework.